So today then, we're going to build on the work that we started last lesson by looking at two more advanced quality control measures that are used in industry. So let's have a look then at today's lesson objectives. Very similar to last week. The first one, you should know what quality control is by now. It is an incredibly important objective, which is why I'm keeping that one the same. If you're not sure what it involves, please go back and have another look at last week's lesson. We also started to look at some quality control methods last week that are used in industry. We're going to have a look at a couple more today, and for each of these you need to be able to explain how they work. That's the key part, not only for your coursework, but this can come up in the final exam as well, so you definitely need to know that. Today then, we're going to continue looking at non-destructive methods of quality control. Remember, these are the processes that do not damage the product, and that means every product could be tested and then go on to be sold if it passes every test. Last time we looked at the two most basic methods, visual inspection and dye penetrant testing. Both of these tests were very easy to perform, but they could only identify simple faults on the outside of a product or a piece of material. To find the faults inside the product, manufacturers have developed some clever tech to help them. The first piece of this clever modern technology that we're going to look at is ultrasonic inspection testing. Ultrasonic inspection testing uses sound waves just like those that we use to hear to build up an image of the inside of a product or a piece of material. In this case though, the sound waves are really high frequency, somewhere between 500 kilohertz to 20 megahertz, and that's outside of the range of human hearing, so we can't hear these. It actually works in the same way as parking sensors that you'd find on loads of cars, or an ultrasound scan used in hospitals. So ultrasonic testing uses a handheld source and detector, or emitter and detector, and it's just like the one that I've got here. We've got the source, or the emitter. It's basically a speaker that sends out these really high-pitched sound waves that we can't hear. And the microphone is the other one here. That's our detector, and that can listen out for these really high-frequency sound waves. And it's commonly used in industry to check materials for any internal defects, such as cracks or hollow areas that could weaken them significantly. And if I were to do this, I could take my emitter and detector and I could press them up against a piece of material and send out a sound wave, a little pulse. That sound wave will then travel through the material until there is some kind of change. This could be a crack or a hollow pocket, or until it reaches the other side of the material. When they hit any difference inside, it causes that wave, that sound wave, to bounce back and reach the detector. So the sound wave gets sent out by the source through the material until it hits a problem. Any problem causes that to be reflected back, just like in a mirror. It bounces back and gets picked up by that detector. And by knowing the time between when you send out the pulse and when it gets reflected back and picked up, a computer can work out whether there are any defects buried beneath the surface of the material. And it can identify exactly where those defects are. And this method is called reflection. Alternatively, you could have your piece of material like this one I've got here and have the emitter on one side and the detector on the other. This time, the detector listens out for the gaps in the signal, as any gaps would mean that the defect inside is bouncing back the sound wave and stopping it reaching that detector. And that method is called attenuation. Now, you don't need to know the names of these for your exam. It's just to help you understand two methods that we could use. The most common one though is reflection, and that's what you can see on the diagram on screen now. The source and detector are side by side and they are pressed up against the surface of the piece of material that you're testing. Now, both methods are incredibly useful and they offer a huge number of advantages to any manufacturer that uses them. Ultrasonic inspection testing is completely non-destructive, as the sound waves pass through the product harmlessly. This means that it's possible to check every single product for defects, And that's a huge benefit, because remember, manufacturers don't want any faulty products making it to their customers. So if they can check every product before they get sent out, they should be able to highlight and find any damaged or defective ones before they make it that far. This method also means that you don't have to cut open the product. Normally, to find any internal defects, you'd have to cut open the piece and try and find them manually. But of course, then you can't go on to sell it. This method also doesn't use any chemicals which could damage the surface. Some of them might be a little bit vulnerable to the dyes used in dye penetrant testing, which means it wouldn't be suitable. This method also allows you to measure the thickness of materials or something like a pipe without having to access both sides of the material. The traditional way of measuring the thickness of something, let's take this piece of aluminium here, would be to use a pair of calipers like these. And if you look, we have to measure from both sides to make it work. You can see the calipers reach both sides of the material. If I wanted to do this on a massive sheet of material, I might not be able to get to both sides. Or if the pipe has already been installed, you might not want to cut it open to check the thickness. Instead then, we can use the ultrasonic array. We've got the source and the detector on the same side, and we can wait for that signal to be reflected back and work out the thickness. So you only have to touch the surface. And if you see the other picture on the page now, you can see that we're checking the thickness of this pipe using a handheld device, and you get a little reading on the screen that gives you your result. This form of testing is entirely safe for workers to perform, and they can do it on a regular basis as there's no danger to them whatsoever. And if it's set up correctly, it can produce incredibly accurate and reliable results. However, despite all these benefits, there are still a couple of drawbacks to this type of quality control. The machines themselves can be incredibly expensive, so the upfront cost to the manufacturer might put them off. It also requires a highly trained and skilled worker to operate, and this equipment is really quite complicated. And that means you've either got to retrain existing workers, which is going to cost you money, or you have to hire skilled workers that might want a higher salary. Also, each time you want to use the machine, it has to be correctly set up and calibrated, especially if you're going to swap between different types of material. And that could take quite a long time to set up, especially when we compare it to visual inspection or dye penetrant testing, the two we looked at last lesson. The other thing to bear in mind is that it might not work with every type of material. Things like paper or wood are not suited to ultrasonic inspection, which means for certain products a different solution might be needed. So it is a really useful way of inspecting a product, especially if you want to try and find some internal problems, but it's still not perfect. Let's move on now then to our second form of modern technology that we're going to look at. So the modern technology that a manufacturer could use for quality control. Remember last lesson, we looked at two basic methods for checking the outside of a product for any flaws. Visual inspection and dye penetrant testing were both great at finding basic problems with products, but they could miss any small imperfections. Both of those methods also rely on human workers to find the problem, and that could lead to some defective products being missed and making it to the customers. Remember, human workers are not perfect. They get distracted, they need to go for breaks, they could spend time thinking about what they're having for dinner instead of focusing on their work, and that means things could slip through the net. And remember, any defective or broken product that makes its way to a customer is going to cost that manufacturer money in the long run. So instead then, manufacturers found a new way to check for these external defects by using a process called 3D scanning. Essentially, 3D scanning uses a laser system to build up incredibly detailed images of the surface of a product. Let's have a look at how this works. So a laser moves across the surface of the product, and it does that really quickly. And a set of very sensitive cameras record the distance and the shape of that laser line as it moves across the surface. And it can do that in all 3 dimensions, X, Y and Z. All of this laser data is then fed into a computer, and that can very quickly turn all of that information into a 3D model of the product. And this 3D model is super accurate, down to thousandths of a millimeter. So it's incredibly accurate and incredibly detailed. You can then compare this 3D model to a CAD model of a perfect ideal part, and from there you can see if there are any differences. And it does this in quite a clever way. If you look at the example on screen now, you can see that a scanned product has been highlighted, and the computer has highlighted any changes. All of the areas in green match that perfect ideal computer model exactly. They are exactly the same as is expected. Anything highlighted in yellow or red is bigger than expected. So that means it's slightly larger than it was meant to be. Any parts in blue are slightly smaller than expected. So it hasn't been quite manufactured correctly. From this, either the computer or a human worker can decide whether the part is good enough to move to the next stage of manufacture, or whether they need to do some repairs or even scrap the part completely. Just like with ultrasonic inspection, there are some major advantages for any manufacturer using this technology. The 3D model that's being created is incredibly accurate, so it can detect microscopic faults with the part or product that could be impossible to detect with visual inspection alone. It can also be used to make sure that separate parts of a product are going to fit together before they make it to the assembly part of the production line. That means when you come to assemble your product, you know that you've only got pieces that are going to fit together. You don't have to waste your time trying to find which pieces fit and scrapping the ones that don't. 3D scanning is also a relatively fast process, and it could be built into the production line so that parts are scanned as they move from process to process. And this, as I said before, could help identify faults with individual pieces before they get assembled. This method is used quite a lot in car manufacture, as you want to make sure all the separate pieces of the car that are being manufactured around the car plant are going to work when they come together to be assembled. You don't want to waste time with 40 pieces that aren't going to fit. And having this as an automated process means that it is far less likely to make mistakes, especially compared to those human workers. It means that the manufacturer, if they wanted to, could replace some of their quality control staff, as they might be no longer needed. Finally, 3D scanning machines can run 24/7 without the need for breaks. So if the rest of the production process could be automated, human workers would not be needed for quality control. And don't forget, human workers cost a lot of money and they can't work 24/7. So if we can automate as much as possible, it can save the company a huge amount of money in the long run and allow them to make more products. Despite all this though, there are still some disadvantages. High quality 3D scanning equipment will cost the manufacturer a huge amount of money to purchase and install, and the maintenance costs to keep it running reliably are pretty high as well, so you've got to take that into account. And even though it could save money by replacing human workers, you will still need at least one skilled operator, and that will be needed to make sure the machine is always running properly. And this could cost more than a standard worker doing a visual inspection. The other big thing is that 3D scanning can still only highlight external faults in the product. If there are any problems on the inside, it still can't find them. You could use ultrasonic testing, but even so, it's still not perfect. So to sum up then for today, we've looked at two modern technologies for quality control: ultrasonic inspection testing and 3D scanning. Both of these processes can offer a reliable way of detecting faults within their products, but there are still limitations. So that's all I'm going to talk about this week.